proven to increase protein synthesis by 150%. That's technically correct, but it may not play nearly as much of a role. Kind of back here. So there's a lot of this stuff that's still out there that we don't fully understand. So, but here's some relationships between acute hormone response and hypertrophy. This is a really interesting kind of where they pulled data from multiple studies out of Marcus Plumman's lab at UAB. And so this is very specifically looking at mechanogrowth factor, messenger RNA, and IGF-1, the sort of regular, the variant that is shared between muscle and liver on all of this, okay? And so what you guys can see is that they broke these people into 3 groups based upon the extent to which, right, they had an increase in myofibular size. So we had responders, sort of like moderate responders, big responders, and then non-responders. And they were looking at, are there differences in kind of the changes over time after one bout or kind of resting levels after 16 weeks of NGF or IGF-1. And what we see is potentially in the very large responders, okay, that we may get a little bit of a bigger increase in mechanogrowth factor, both acutely and after sort of 16 weeks in the midst of all of this. So there may be a little bit of something, okay, a little bit of something to what's driving people that can respond better than others. It may be somewhat related to these changes in these anabolic hormones. But they looked at some other things that weren't just MGF and IGF-1 that they didn't really support as much. There may be a little bit of stuff that goes into there. So again, our story is a little bit all over the place. In some studies, the hormones matter. In other studies, the hormones don't matter as much. In some studies, the protein synthesis rates matter. In other studies, they don't matter quite as much. Okay. So I thought we talked about this before. If you guys haven't talked about hyperplasia, we talked about hyperplasia. We did muscle stuff. No, Matt's like, no, I would have remembered. Okay. So hyperplasia is the idea that you can hypertrophy by taking one fiber and having it split into 2 fibers, both of which can then grow. Okay. And so you get a bigger muscle by splitting your fibers in 2, so you have more total fibers, as opposed to I have a set number of fibers, and each of those fibers can grow a certain amount. Okay. It is practically impossible to quantify this in a person. Okay. We're going to have Richard. I'm sorry. You're going to have to go. We're going to kill Richard. Okay. And we're going to count the number of fibers in one arm. Actually, sorry, I apologize. What we're going to do is we're going to have to take your right arm, cut it off, pull it off out your bicep, count all your fibers there. Then we're going to have to reattach it. Okay. Fix everything up, have you train, cut it off again, and then count all the fibers again. So it's almost impossible. We can't quantify how many fibers you have in your muscle without cutting your muscle out. And once it's out, we can't really put it back. Like my biomedical engineers, we're not there yet. Did you guys see that the things they've created that are like stem cell robots that can now reproduce and things? Like, yeah, y'all got to be careful. It's Jurassic Park all over again. Terminator all over again. Like the robots will come for us. The dinosaurs will come for us, right? We all think about whether we can do it, not whether we should do it. What do you mean by uniform? Like, is your right arm the same as your left?
Are each fiber as big as the other?
No, they are not. Now, in animal models where the animals are genetically identical, they're very similar. But you're very different than Sarah, who's very different than Sai, who's very different than Ethan in that way. Okay. So in animal models, right, if we look at the percent change in the number of fibers, there's the stretch model, there's an exercise model, and then sort of the other model where they're gonna do the synovial ablation. What we seem to see in animal models is that if we do a chronic stretch model, where we cut like the tendon and we stretch the muscle out and then reattach it, and like walk around plantar flex all the time or something, we do seem to see a little bit of fiber splitting in the animals. We don't usually think that that's what happens in people. We're not 100% sure if taking steroids might also cause some of this. So it's hard for us to quantify, but we don't really think, in looking at cadavers and a little bit they've done with all of this, that this is a thing that happens. You have however many muscle fibers you're ever going to have, generally when you're born, which blows my mind, right? Think about how small you once were, right? Every night my daughter makes us like show her pictures of when she was first born. She says, I want to see when I was in mommy's belly, which we don't have any pictures of, but she wants to see the pictures right when she came out. And she's so small. And I think that like she has as many muscle fibers then as she's going to when she's y'all's age or my age. And it's kind of a mind bending type of thing. Okay. So if we don't get hypertrophy by hyperplasia, what is going to happen? So what we tend to think happens is that this is going to occur in 2 phases. Okay. So you have all your fibers, each fiber is going to have this ability to get bigger. And what's happening is that initially in phase 1, we're going to get a bigger fiber, and you're getting more actin, more myosin, more of the other kind of proteins going on in there. And at some point, the fiber gets too big to be properly accommodated by the number of nuclei that it has. So then we enter this phase 2, where we're going to begin to add nuclei in addition to continuing to add myofibrillar protein in the midst of all of this. Okay. And so some of those nuclei may come from satellite cells, some of them may come from replication of existing nuclei. Okay. That's kind of how we think that this is all. All right, so some of the last stuff is just kind of a hodgepodge of other interesting kind of data that I think are out there on kind of what do we know. People often ask, okay, do we see fiber type conversion, and then do type 1 fibers or type 2 fibers, do they hypertrophy to a different extent? Are people that are the super responders all type 2, right? Or are people that have a lot of type 1 have a hard time increasing? What we tend to see in the midst of all of this is that for the most part, all fibers tend to increase in size. Okay, these are some data. These data are 20 years old now, but these we've got old men, okay, in the black. We've got young women and then in the gray, and then young men in the white. These are data from Ball State. I said that out of the trapeze lab. And what you're going to see is this is in type 1 fibers, and the old dudes, they're getting bigger. And the younger, both groups of the younger people, they're really not. We'll talk about why in a second. In the 2As, we tend to see a lot of hypertrophy in the 2As in young and old, or in young men and young women. Very little change in the X's, and we lose all of these hybrid fibers that we're going to see. Okay, so based upon these data, it seems that the type 2 fibers are going to hypertrophy about 50% more than the type 1s. Okay. Why might that both be a real observable thing, but also we could interpret that all fibers have the same capacity to hypertrophy? New critical thinking question right now. What do you want to guess?
Type 1 fibers are already smaller.
In a lot of instances, they're already bigger. Far more often when gay. I'm just walking, I'm recruiting my type 1s, right? So typically, one of the things that we think may happen is that because you use your 1s so much, it already hypertrophied them a fairly significant amount. And you don't use your type 2s nearly as often. And so they're going to start off in most people at a smaller relative size compared to their genetic maximum. And that may account for this. Because if we do detraining, we seem to lose as much in both. And then the ones kind of come back after weeks with retraining. So there's some interesting stuff that goes on there. There's some other data that shows that they all kind of increase to the same extent. It really depends upon whose lab you want to believe, on the age, on the state of training, and a host of some other things. Okay. The next little bit of stuff, we're going to talk about satellite cells, which I think are really fascinating, really cool. Even though at least in our kind of labs here, we can't do a lot with them. So what I'm going to show you guys, these are some data that they've done some really fun stuff. These are myogenic stem cells, right? That's what satellite cells are. And so we know that they're important for regeneration. And that it's this IGF-1 MGF axis that appears to kind of drive and interact with those satellite cells. What you can see here, these are animal model data. And so what you can see in the black, okay, is they took these mice and they irradiated them, okay? So they zapped them with radiation and that killed off their satellite cells, okay? Killed off their satellite cells. Then they did what's called synergist ablation. So they basically cut their gastroc and they had to walk around using just only their solids. Okay. So here's no satellite cell function plus the training stimulus. Here's just the ablation model, so just the training. Okay. Here's just irradiating, so we're just going to kill your satellite cells, and then there's nothing. Where you get neither of those two things. What you can see is that when we knock out the satellite cells, whether you're getting a stimulus or not, your muscles shrink. You lose the ability to grow, you lose the ability to repair and regenerate. So this was the beginning of these ideas that, oh, these things must be really important. Okay. These are data that are almost 30 years old. We haven't known a huge amount about all of these kinds of things previously. Okay. So this is sort of showing what we want to see in all of this. This is mechanogrowth factor messenger RNA. Okay. And so what we're going to get out of all of this is sort of, it's been repeated this particular portion of it. And they were looking at the fact that in both the overload, what they're getting in the irradiation side, they're getting similar increases in mechanogrowth factor. We found stuff that looks a whole lot, it looks just like this. And so part of their idea was that these people had the irradiation didn't affect the mechanogrowth factor. It's still going up, but we're still not able to then activate satellite cells. Okay. And so there's some really interesting stuff that's kind of been done. Okay. So part of what we know about activating the satellite cells is that there's going to be some interaction with the nuclear DNA in a muscle fiber. And this is a kind of rough approximation, okay? A rough approximation of some of the important intracellular signals that we think are going to lead to formation of messenger RNA and its translation into sort of actin and myosin or molecular protein kinds of lines. So you can look at all of this. We're talking about growth hormone, IGF-1, binding on insulin-like receptors. Okay, going to signal through all of these other different things, and they're going to get sort of put in here at something called mTOR. mTOR stands for the mammalian target of rapamycin. Okay, so this particular thing, mTOR, can be knocked out by giving the antibiotic rapamycin. And so what we know is that we're going to come through some of these things. We think there's potentially a mechanosensor, right? And the mTOR is going to possibly get these phosphorylations, and it's going to activate P70S6 kinase, which is then going to help us kind of downstream this. And there may also be some level of regulation of things by glycogen depletion and reductions or elevations in AMP. it's going to activate the same kinase, and this may lead to some inhibition. But mTOR is the big thing. Okay, so if we look at some of these molecular pathways, okay, what we're going to look at is there's a thing called protein kinase B, otherwise called AKT, which is a downstream target of testosterone and growth hormone. We also have mTOR, and then we have what they're going to call S6, P70S6 kinase. And all of those things are going to work in concert with each other to hopefully lead to increases in protein synthesis rates. So here's some so this is, you guys know what knockout mice are, or knock-in mice, or things like that, where we can either take like one gene or one protein and make it all go away, or we can take something and we can add a particular gene in. You guys also know what transgenic mice, or transgenic rats are, right? And so essentially what we've done here is we have a mouse where we've overexpressed, okay, this AKT signaling molecule. We've overexpressed protein kinase, okay? And they've done that. That's what the TAM, which I've forgotten exactly what the TAM is, the abbreviation. This is the sort of substrate that we're using to overexpress AKT. And what you will note, these things aren't exercise. It's just here, express more AKT, and your muscles get like twice as big. Okay. So if I can take Ethan and we can overexpress and turn on his AKT pathway, boom. Okay. Here we go. Let's get jacked. Okay. Now we know in humans there are genetic variations, and they're individualized. What's the word I'm looking for, Gabe? You're the genetic person. The little differences in the pardon? Genes, SNPs, something. SNPs, right? You can do a genetic test. Ancestry does it, or what's the 23andMe, where they do a little stuff. They do your DNA. We can look at what do you have the AKT gene variant that leads to you're going to have more expression of this than somebody else. And it's predictive that you will likely be a person that will have larger muscles than those other people. So we know that some of these things are linked. Okay. So we know because of all of this, then that this AKT is clearly involved. Some really early work. This is from Subodin, who is a huge fucking deal. These are some of the first ones where they blocked mTOR, and they can block hypertrophy. Okay. And so what you can see again, this is animal models, and we've got people that they're doing, they've got these things and they're doing the synergist ablation deal in them, and then they're basically cutting the synergist, and we see this, and then they give them rapamycin. And what you will note is that at 7 days or 14 days after the ablation, we're blunting this increase in muscle size that we see from all of this by giving them the rapamycin. So this is muscle weight. This is actual cross-sectional area in all of them, and you can see the black is the control, and you can see these other ones. So by applying rapamycin, we can knock out mTOR, and we can essentially knock out the hypertrophic response that we would normally see from all of that. So again, these are some of the first works we're like, oh, mTOR must matter. Okay. So similar things, okay. These folks then, this is out of Troy Hornberger's lab at University of Wisconsin. They had mice where they can give rapamycin, blunt the hypertrophy, but then they can essentially, they genetically engineered mice that they have an mTOR that becomes insensitive to the rapamycin. And so when they have that version, then it rescues their ability to have all of those. And we know that mTOR, in addition to causing hypertrophy, mTOR increases ribosomes. So that may be one of the ways that it's going to play. It's going to drive sort of transcription of messenger RNA. It's also going to lead to an increase in ribosomes, so we can do more things with all of those. So what you can see basically, here's our wild type mouse. where we've got the synergist ablation. So this is our control here. This is synergist ablation with no rapamycin. Here we have just rapamycin, and we've got synergist ablation and rapamycin. What you want to look at is these two things, okay? If we train them or we give them this idea of training, rapamycin wants it. But here we have our rapamycin resistant mTOR in these models, and we do it, and basically now we've completely rescued all of that stuff. Okay, so for those of you that ever do animal model stuff or you do cell culture stuff, it's a very, very common kind of reductionist methodological way of figuring out what does something. So I block it and I take it away. Okay, do I lose the function? Do I lose the adaptation? Then I block it, but then I turn back around and I add the thing back in on top of all of it, and then can I rescue that particular version of function? Okay. This is a very, very common way of trying to isolate those things. So like imagine, okay, let's just say we're going to take, I'm sorry, Cy, we're taking the bullet this time. We're going to take Cy and we're going to zap him with a bunch of x-rays, and we're going to knock out his testosterone production entirely. Okay. And then we would look at it and see like what happens when he resistance trains. Okay. Then we would wait for a while, we would do that, and then we would give him testosterone back to some physiological level, and we would see then if it rescued that particular. Give us some idea of not only when it's not there, does it go down, but if we give it back, does it go back up? It kind of lets us attack the problem from both sides, which is one of the kind of classical experimental ways to determine function. Okay, it needs to work from both directions. Okay. So, kind of an interesting thing. So, one of the questions that we've still not fully elucidated is what is it about exercise that stimulates mTOR? We know that it does, but what is it about all of this? And what people have been looking for, we know that there are growth factors that IGF-1 and MGF and growth hormone and things are going to signal in some ways down through mTOR. But we also think that there is some sort of what we would call a mechanoreceptor. There's something that is sensitive to force being produced across the fiber membrane, okay? And it needs that force to disrupt it, okay? And that may then sort of lead to some of the kind of secondary activating things they're going to turn on mTOR, okay? It's a very, very kind of, it's a very, very sort of involved process that's going to go on. So like we can give this thing called propanin, and we can block basically the effects of PI3 kinase. So you can stimulate with growth hormone or IGF-1 and then give propanin, and it blunts all of the activity of all of those things. And so we can knock out the ability of those things to turn on mTOR and then try to look at some other stuff that may be getting turned on with without contractions. We've not fully worked out what this exact sensor is, but I imagine that we will. So, okay. Last little bit here, and I'll tell you a fun story about one of our interactions when I was a PhD student with Procter & Gamble. So there is a thing, it's an anti-growth factor, and it is called myostatin. Okay, myostatin. What you see here, this is a Belgian blue bull. Okay, if we were at Texas A&M, everybody would know what this is. If we were at Oklahoma State, in that school, they might have a better sense of sort of these animal genetics and all of these things. This bull lacks myostatin. He just rolls around and he is jacked. Okay, myostatin, okay, is a naturally occurring protein that blocks the ability of satellite cells to function. So if you have a lot of myostatin, okay, that's going to put a limit or a governor or a cap on how big your muscles can get. If you have basically no myostatin, which people genetically have this wide range of these things, no myostatin, you look like this. Neuromyostatin deficient, pretty much any animal you can think of, just Google it, just be prepared. You see the myostatin like mouse, they've got them all laid open. I mean, it looks like freaking Mighty Mouse. which you all probably don't know that reference or the cartoon or anything. So there was an old cartoon called Mighty Mouse. There are myostatin deficient people. Okay, there's a myostatin baby. I can tell you as someone that had a baby, babies don't have visible vastus lateralis. Okay, not a thing that they have. Babies are soft and squishy and they look like the Michelin tire baby and all of those things. And then they grow up and they're not quite so squishy anymore. And it's sad. Okay, there are myostatin deficient people or people with very low myostatin levels. Surprisingly, a lot of them are Olympians. And so you just genetically have this ability to have a lot of muscle mass. So when one Olympian has a baby with another Olympian, then they make babies that have very little myostatin. Okay, so I imagine, and if anybody knows this or not, you guys can weigh in. I imagine that part of some of the next frontier in doping is not that we give you testosterone or growth hormone and then have to try to mask that like you do female fertility drugs or anything else. It's that we're going to find a way to knock out your existing myostatin function, right? We're going to give you a myostatin inhibitor. And then all you've done is lower myostatin. I don't think that WADA or anybody looks for those things. Actually, I don't think that the NCAA. So you guys didn't have to get blood, right? It was just urine. Go over and test it. Yeah, it's just so they've decided somehow blood is the lie, right? That's where your privacy starts, is with blood, not with urine on those things. But I imagine that's kind of where people will go, is to look at those kinds of things. They probably already are. Pardon?
What are the long-term effects, the life?
I have no idea. I don't know. I don't know if our Belgian blue bull, what its lifespan is in comparison to a regular one. I don't know if bulls get cardiovascular disease or I don't know what, other than going to the slaughterhouse, I don't know much about the life cycle of cows and those kinds of things. My guess is that, there might not be some great things that could be side effects of that, but I don't know. Ooh, I don't know. I'm not sure what role it plays in cardiovascular hypertrophy. It's a good question. I mean, cardiac muscle is kind of like all other things. So what could happen is maybe if you don't have myostatin, you may get more concentric hypertrophy, and then that could lead to sort of hypertrophic cardiomyopathy. Maybe. I don't know this.
Are there the same kind of satellite cells on cardiac muscle?
I don't know the answer to that. Somebody should Google. Now we have good critical thinking questions for your final. Figure out if there are as many satellite cells in there. Do they express myostatin? And what should we learn from all of that on those things? Right? Drew wants to be a bodybuilder. He's come up with this new thing that Matt has engineered for him to block myostatin. And so now we're going to get huge. So sorry, you had a question. I'm just,
Oh, no, that's fine. The bodybuilding ship is still. But,
okay.
How about so our final is like December 19th or something like that. Is our take home going to be after that?
Cardiac muscle does not have equivalent cells to satellite cells.
Okay. So it does not have equivalent cells. Thank you, Jordan.
Yeah.
What is a regular bull lift? 20? Okay. Anybody is like tired that the world is going to hell in a handbasket when you are on Twitter? There's an animal sanctuary in upstate New York. They have a cow whose name is Crouton. And the Twitter account, it's like M_Crouton. They do a nightly video where they go out and they feed the cows and the horses, and they have all these pigs and things, and it's very sort of soothing. My wife and I found it in the middle of the early part of the pandemic. And so it's like our nightly thing as we watch what is Crouton doing. They have donkeys, they have all kinds of things. It's great. So anyway.
I mean, I watched what's her name, Fiona, the hippo.
Oh yes.
Yeah.
At the Columbus Zoo.
Yeah.
Yes, or is she in Cincinnati? I think it's at Columbus. Is it Cincinnati? I know what you're talking about.
Yeah. Little baby hippo.
She's not a little baby.
No,
She's all
but
big.
she's a big baby. She won't little at all.
She's a hippo. What do you want her to do?
Hippos are cute. I have one.
They are. Hippos are lovely. So
I'll have a tough one.
Okay, I'm sorry, Drew. We totally got a feel from your actual question.
Oh, I forgot.
Your question was, if our test is during finals week, on what day is it supposed to be?
Thursday.
So it's on Thursday, the 16th. The question was, when is the take-home portion?
I think it says the 19th, which is a Sunday.
Because grades are due on Tuesday of that week after, which is the 21st.
You could
But
make it
it's-
easy on yourself. if you don't wanna take home test.
But if it didn't take, if the take home was due the day of the.
The in-class portion, then you might know what to expect on the in-class portion, not with the stuff that was on the take-home.
Well.
Well,
Not that smart.
Okay.
Yeah, exactly.
All right. What if we do this?
Yeah.
Okay. What if we do this? What if, rather than having the in-class test, we just have to take home?
Yes.
Yes.
Are you serious?
And we'll make the take-home test due on that Thursday or whatever during finals week, so I can grade it on Friday and be fucking done.
So then when will?
There will
it
not be an
open?
in-class portion. How about that? We just take home.
When will it open?
So if we have our last day of lecture next Wednesday, my assumption is that I will open it on Wednesday
Yeah.
after class.
Yeah.
Thank you.
How does that sound for you?
Yes.
Because I know like those of you guys that are in stats, y'all have a test next week. Those of y'all that are in endo have a test next week. My biomedical folks, do y'all have tests next week? Do y'all have tests during actual
I have
finals?
one.
Today. That's your final, sir?
Nope, that was the midterm.
What?
Midterm, she's like, okay.
Yeah.
So hard.
So does that sound like a reasonably fair thing? That we'll just do that. Yes, sir.
So you said open next Wednesday? Was it next Wednesday?
And it will be closed Thursday after that. So you'd have like a week basically to get it done.
I know.
Okay. I don't want to have to grade things. That's the part afterwards. Yeah. Luckily, in some ways, that we just haven't covered so much stuff. I mean, it will basically be resistance training and stuff we're going to do next week. Not that much stuff. So, okay.
What are we doing?
We're going to talk about what I like to call integrative control of exercise performance. So if you're going to go run a race, who's going to win? What physiological variables and all the things we've already talked about can we put together to try to decide can Gabe beat Josiah at a race or not? That's going to be next. There are not critical thinking questions for that, I don't think. So, so I will need your critical thinking questions for resistance training at some point. At some point. Gabe sent me his, I don't know if anybody else has given theirs. Talk about it. If you've got them, I will happily take them. If you don't have them, that's also okay. We've all reached the end of the semester and I think we're all just tired. Yeah, just email it. I'm just trying to get through. I got a master's student do their thesis proposal in the morning. Just trying to get through that. You guys think y'all are nervous when you have to do those things? We're also nervous. For you guys, for ourselves, for everyone. So. Y'all are going to get an email. We're supposed to give you guys time in class to do this, and I guess I can. So you're going to probably have gotten an email and get a notification on Canvas. So we are participating rather than the normal course evaluation that you get for all your other classes. In our department, we are part of the piloting of a different and somewhat more qualitative evaluation of teaching effectiveness and things. And so should have gotten an email linking you to the survey. But it's going to ask some more in-depth questions than just simple things like rate the teaching effectiveness, rate the useful, how much you learned in this class compared to other ones. It's a little bit more kind of deeper types of things that are there that are hopefully going to give potentially more meaningful feedback to us. This is the second year in a row that we've been a part of this. Get some other extra interesting data. My sense of the university is going to go to this rather than the other way of doing it on those kinds of things. So even my grad students, if you teach for us, y'all are going to be evaluated the same way, the same kind of thing. You shouldn't have to send it to your students. What they encourage us to do is to give everybody time in class to complete them. And then usually if you're an instructor of a class and you get like 90% of the class or greater to actually do it, then you can enter like in a raffle and the university will give you an iPad or something. Usually have several somethings. You don't get to keep the iPad, it's still the university's iPad. Like, hey, we'll give you this thing. I would be able to give away like travel money or something of like actual somewhat more value than an iPad, but it's better than nothing. They try to bribe us to get you guys to do this. You're gonna get an email. I would appreciate your honest and attentive, thorough feedback. Lots of things that we do in class, I think I said at the start of the semester, now have come out of suggestions that people have made. The way we do the critical thinking stuff, the way that we do the quizzes, the way that we have learning objectives, the fact that we went from one day of class to 2 days of class, all of those things, I used some of the feedback from the stuff to go and try to argue that this was potentially. So if there are things you like, tell me that. If there are things that you don't like, also tell me that. Just remember, I'm also a person who has feelings. And so just, just nice-ish. Negative ones, those who have never had teaching evals done yet, negative ones are the ones you always remember. So I was told once that they hoped that no one ever had to take me class ever again. It was the single worst instructor they had ever had in their entire life. I should not be allowed to teach them. It's not. It's here. This person here said that. I'm pretty sure I know who it was. It's surprised.
Is it handwriting?
Huh? No, they're all typed out. We don't get the results until we won't get the results until grades are submitted and those things. It's all completely anonymous. Everything is it's all just typed out. We don't know who's taken it and who hasn't taken it. But there's no information provided on those kinds of things. So just say whatever you like. Appreciate it. Anything else? No? Anybody got any bro science we can do here? Our last 15 minutes. Or if you guys just want to leave. How did our stats presentations go, everybody? It went okay?
Yeah, they're supposed to be great. I don't know.